Okay, that started. Short announcement. Maybe some of you have heard it before, but just in case you're not in 4308, I do have some specified times to be available for questions outside of regular class time. And that should be Mondays and Wednesdays, pretty much right after this class. And it will go potentially for at least an hour, but the point is if you don't join in on the Zoom for 15 minutes, I'm assuming there's no one interested and I'm probably gonna pack up and go home. However, if your questions are coming in, we'll go as long as an hour. Usually that's enough. And then that's for Mondays and Wednesdays. So I'll stay plugged in for 15 minutes automatically. On Fridays, I'd appreciate if you think you're going to need me to, or you need some questions answered, I'd request that you just let me know, and I'm happy to be here and stay longer on Fridays. But otherwise, if I don't think there's any questions coming in, then I'm more or less inclined just to pack up and start the weekend early. Any questions about that part?
No.
Let me see, I'm trying to hear, I didn't hear that last, was that a question?
I was just saying no.
Okay, you might need to turn up your volume a little bit. I'm not catching, I'm hearing the question, but I'm not hearing it clearly enough.
He just said no to your
okay,
question.
that's good.
If there was any
that's
questions.
Fine. Okay, let's see. The next item on the agenda would be to take a look or give you a chance to ask some questions on these homework problems. That would be homework number 4 from 4311. Did anybody have any questions from those?
Yeah, I just had a comment. There was number 7.
Number 7.
That's okay. That 2.4-9
okay.
Wasn't the question, it was 2.5-9.
Oh, okay. So I got it's 5-9, not 4-9.
Right, and then the last part of number 7 is actually the question number 8. It was repeated.
Oh, okay. So just making sure, according to your records, if I change and I'll double check this to make sure it's correct, but you're saying you think that should be a 5 there?
Right.
Okay, I can take care of that. And what's the other suggested change identified?
The end of number 7 where it says based on 2.5.1 is actually the question number 8. Just the whole thing needs to be taken out of question 7.
Ah, yeah. I see your point. In other words, that second part of number 7 is really number 8. Is that what you're saying? Is that what you're saying?
Yes.
Okay, I'll confirm on that, but that seems like it probably makes sense. All right. Thank you for those comments. Yep. And I'll fix those on Canvas when I get a chance, when I get back home. All right, any other questions? Okay. Well, we want to, I guess, keep the ball moving on the chapter we're in. And if I'm not mistaken, last time we pretty much used up the time to just remind you, there's actually 3 types of Fourier series that are, oops, you can't see it because I have it in the right place. There are 3 types of Fourier series that are discussed in the chapter. The so-called basic trig type, which usually is the first one you see. Then the compact trig. And then from the compact trig, we can jump to the exponential, turns out. And so that the transition kind of goes like that. And last time, we actually came up with the agreement, hopefully agreement if we look at it, for the formulas for the AN and the BN using this concept of inner product. And that's about where we were, and then we didn't quite get to the one for the A0. But our plan is to start that today on page, I think page 7 of the notes. Okay, so let me put that in my pocket here. So on page 7, okay. Now, just to remind you, the approach we're using to explain these formulas would sometimes it's called kind of like representation theory, where you have what I call a basis set. In this case, it's functions, not vectors in space, but the concepts are similar. So we'd come up with these formulas last time, and if you just take a quick check, they are the same as the ones that are in the table for the Fourier series. And so we want to, and a part of that discussion, we introduced the idea that you can think of in terms of representation theory as the cosines and the sines and a constant, in this case 1, serving as some sense a complete set to represent any function. And our approach was, here is our hypothetical representation for the signal in terms of the sines and the cosines. And from there, we proceeded to extract the AN and the BN formulas, the formulas for those coefficients. And the last one would be the A0, which one could argue we could have done first. So we're going to go down that same path in terms of concepts. So one of the, see it's on here, one of the important ingredients that we used was this definition for an inner product between two functions. And we used that last time to come up with the formulas for the AN and the BN. And we're going to use it again here. Okay, in this case, it's for the A0. So in order to get that expression for the A0, what we're going to do is we're going to kind of the same way, we're going to do the inner product on both sides. Okay, now in some sense, I'm thinking of coming in from the left, so that you get the one inner product x of t, and then that one inner product operation is being a linear operation. You can pretty much think of distributing it to every one of the terms. So as you distribute it to every one of the terms, it moves past a sum being linear, moves past a constants being linear. So you just simply get the that inner product operation with the time dependence needed on those parts that have time dependence. Any questions so far? Okay. Now if we were going to write out what this would mean for the particular case, the far left, this is what it would translate into. Basically just that one, which is a constant, just translates into the traditional one in the sense of the properties with multiplication. So so we would just replace that F star itself that appears there with simply 1. and the g of t, then it becomes simply the x of t. As complicated or as simple as that is, that's kind of how it goes. But if you have a question, bring it up. So that's the left-hand side. Now on the right-hand side, okay, that's this side here. We then look at the individual terms. Now we're not going to look at all of them simultaneously, but we're going to look at them individually here. So we would argue that if we in fact looked at the inner product with a cosine as we see it and with a sine, the arguments here are the idea that we're claiming here is that you're going to get 0. Now, if I'm going to write this one out for the cosine, and then if you still have a question, we can go into more detail. But let's say I just wanted to write what that would mean in terms of this inner product. Well, we know that 1 as a number is real. Therefore, the effective f of t is simply 1 itself. And so we know if we integrate t naught, the cosine of n omega naught t dt, what should that equal?
0.
0.
Yeah.
Right, 0. Any questions on that part? That's because, right, we even had a picture last time that was guiding us into these kind of situations where we had the picture which looked kind of like this. And that represented the fact that as long as you're integrating an integer number of cycles of a sinusoid, it doesn't matter if it's cosine or sine, the area averages out to 0. So that's why, and you can make the same kind of argument for doing it with a sine, right? So that's why we could say, well, that's going to be 0, that's going to be 0. So in a sense, we've knocked out the middle term, we knocked out the term on the right, and all we have left then to thank goodness there's something left to solve for the A0, we have this one, the first term. Okay. Now, there's kind of a trick here in a way. I mean, what we're saying is that constant A0 can be simply thought of as A0 times the function represented by 1. Okay, as we know I think we know it's right. So the A0 itself can be kind of pulled to the left and ignored temporarily, even though we're not throwing it away, and just work out the inner product between 1 with itself, and of course the first one, it being real, means it doesn't change. It's simply 1 itself, and the second one is 1. So really, this is my. If you want to go back at the top, this is my F's complex conjugate, and this is my G. And we plug it in to that recipe, and we know that what this means, and that just gives you A0 times T naught. Speak up. You got a question? I'm thinking I'm not going too fast, but let me know if I am. Okay, so what is the bottom line on the results? Well, we've established that in this process, what you get on the left looks like that integral, okay, which we show here. And what you get on the right when doing this inner product just simply becomes A naught T naught. And so, and since our objective is to solve for that leading coefficient A naught, when we do it, we get this rule. And the common interpretation for that is you're integrating a function over a certain interval and dividing by that same time interval. That's like computing the average value of the function. And of course, if we take a look at our table, we see, in fact, that's the same rule we have here. So the sequence of steps that we've taken have now essentially generated the arguments and the expressions that we have here for sometimes called the basic trig. Any questions on that?
No.
Is that a question? No. Okay, it was no. All right. All right. Now, what we want to do is we want to use our understanding. What we're going to do is we're going to take our representation for the basic trig and manage to revise the form in such a way that it ends up being the same as what we see here, the compact trig. And presumably when we're done, we'll have confirmed the recipe that's associated with these coefficients. So we see that the compact trig coefficients are in fact related directly to the ANs and the BNs. And this phase is associated with that representation are also related to the ANs and the BNs. Okay, so I think you see our objective. I don't know if you know, I understand you don't quite yet see all the details because that's why we're going to go through it. Okay, so compact trig case. Now, kind of keep in mind, omega sub n here really represents, specifically for this case, n omega naught. Okay. In other words, harmonics of the fundamental for this case. We're doing Fourier series. Now, our objective is to realize, okay, our objective is, of course, to come up with the recipes for the C naught and Cn. But to realize and to get there, we have to realize that we're looking at representations for the same quantity on the left. All right. So whether you elect to use the basic trig or the compact trig, the idea is that really it's, even though the representation is different, it's an equivalent representation. Okay, so the left-hand sides have to be the same. Okay, so the first observation, which really helps a lot here to make right off the bat, is one that is, we're not going to prove it. I think it doesn't need a fancy proof. I think you could just argue that you can understand it. And if you can't, ask a question. We're simply going to say, well, here we have a representation. Let's see, the original basic was constant plus AN and BN times sinusoids, all time dependence. And in the compact trig representation, it's constant plus, again, the sum of terms which, strictly speaking, have time dependence. Okay? So, I mean, if it didn't have time dependence, it would have to be lumped in with the constants. So the argument here is, it's actually as simple as complicated as you want it to be, but the argument is that, well, because all the terms here are terms with time dependence, in order for these two to actually be the same, the only way that is possible is that C0 has to equal A0. It's the only way you can imagine it being possible. And it's certainly quite plausible. Any questions on that? So without a lot of fancy proof, we just simply say C0 is equal to A0. So the leading coefficient has to be A0. Okay, so I'm not hearing any arguments on that one. All right, now in order to go down the path of getting the expression for the C sub n, we will do the following. We will define a C sub n this way. Okay, now make sure, I want to say this turns out, it'll turn out to be the same C sub n. But just imagine you define a C sub n such that it's defined as the square root of the sum of the squares associated with the AN and the BNs from the basic trig, and using that recipe. That's all I'm saying. All we're going to say is, well, let's imagine we defined a CN that had that recipe. Now, the first thing you could probably conclude is, well, the CN has to be both real and positive. And I'm not, hopefully, if you have a question on that, bring it up, but I'm going to claim that's true. But also, I would, since these are squared, of course, you would expect that the CNs are actually going to be bigger than either, at least, one way to view this, it's, the CN is greater than or, let's put it, is greater than or equal to either the AN or the BN. Okay, so in other words, there's no way that the AN or the BN could be greater than the CN, is my point. Okay, so that way we would say, well, if we can make that claim, and of course I think that's consistent with the formula, we can always say that AN over CN it's got an upper bound of 1, and the BN over CN has an upper bound of 1, based on that recipe. Now, we'll see in a minute that observation is helpful, extremely helpful. Now, we'll go back to the basic trig and rewrite it in the following way. We'll take into account that we've already figured out the A0 has to be the same as the C0, so we'll put that in. We'll take the liberty of doing that. And we'll multiply and divide by Cn. Okay, so we really didn't change the expression. So really it is, this part right here, okay, is the same as this part. Notice that if you let the CNs cancel, you go all the way back to here. Okay. Now we see we've got a cosine n omega naught t and a sine n omega naught t. We see, in fact, that the factors in front of both the cosine and the sine there have to meet this condition. Therefore, they're less than or equal to 1. So we can imagine that this form right here is in the form of a cosine times a cosine plus a sine times a sine. Now let's allow me the liberty to define that. In other words, we'll say that the cosine part of A is dictated by the cosine that appears there evidently. And we'll define the cosine of B as being the AN over CN. And we'll define the BN over CN to be the sine of B. Now notice if you do that, notice this is sine of A, and this is the cosine of A. And if you make that association to what I call the trig counterparts that go with this figure, then you could say, well, the AN over the CN plays the role of the cosine of some angle B, and the BN over CN plays the role of the sine of some angle B. And I'll leave it to you from your being experts in trig. You'll see that, in fact, this picture right here representing a right triangle is, in fact, consistent with that interpretation. In the sense that we could say the cosine of B should be the adjacent over the hypotenuse. Okay, coming back over here, the adjacent is A sub n, hypotenuse is C sub n. The cosine of B is AN over CN. And I would argue from here, the sine of B is opposite over hypotenuse. And here we see we got the Bn over Cn giving us the sine of B. I go through that too fast. Not hearing any questions. Any questions out there?
No, sir.
Okay. Assuming that's a no for everyone. Okay. Now, I'm not assuming you had this memorized, but if you did check your favorite trig book, you would trig identities, you would find that this one, in fact, does fall into a well-known category, and it would represent the cosine of A minus B. And I'll let you confirm that with your favorite trig book. Now, the fact is that you can represent that this way, which suggests, okay, we can replace those some of those two terms with just one term, which would be the cosine of A minus B, where the sine of B and the cosine of B follow that guideline, and the A is n omega naught t. So if we just for the moment, let's just say we then say cosine of A minus B, we can go ahead, since there's nothing to stop us from doing it, we can get rid of the A in terms of something more physical. We'll put in for the A, the n omega naught t. We still have the B there, of course. Now to get the B, we go back to the right triangle we have here. And since we know that the tangent of B would be the opposite over adjacent, the inverse tangent of the opposite over the adjacent will be the angle B. Now, one caveat on that. That is that you've got to be careful, like we did with complex numbers, to get, since there's a full 360 degrees, you have a situation not unlike complex numbers, which we've already talked about various places, that if the real part happens to be negative, remember with the complex numbers, we had this rule where we had to either, and it doesn't matter whether you add pi or subtract pi, it turns out you end up with the same spot in the 300 degrees cycle. But the point is that we would have to add that caveat in there. If the AN happens to be less than 0, we want to have to get the correct answer, we need to either, and I guess it doesn't matter, either add or subtract 180 and should have an equivalent answer. But we want to include that as part of our recipe. Okay, and if you would say, well, how can you think about this? Well, think about the same issue that comes up with complex numbers in the complex plane. And if you remember that, remember we had the same kind of rule. So, now, if we take what we have right now, okay, so if we take our result here, okay, and kind of bear in mind, we've replaced all of this with the cosine of A minus B. And there it is right there. Okay, that's what I want to, and we already placed the A with the n omega naught t. And then we get the minus B. And what we want to do is we want to say, well, ultimately our goal would be to say, well, our compact trig representation has the form that it takes has been decided for us, including pluses and minuses wherever they appear. So we have in essence, we've come up with a recipe for C sub n, which we now have here, but we need a recipe for that angle theta sub n. So one way to think about this is if we took this result right here and we plugged it back in, you know, up into here, okay, we would end up with this, right? N omega naught T minus B. There's the N omega naught T minus B, complete with this sum, okay? And the idea would be then, well, we want to force this form, which we came up with, to be identical to this form at the top, which is the standard form for the compact trig. And the only way we can force them to be the same is to recognize, then if you, one way to view that is a minus B has to, the negative of the B must be the same, since you're adding here with a plus, must be the same as theta sub n. And you can see that if you replace B with a minus theta n, you go directly back up to here. Okay, this is the right time to ask a question if you got it. Okay. So that tells us that if we want a recipe for theta sub n, okay, that goes up into here, a working recipe for our purposes then would be based on what we've come up with for the B. So if we got the recipe for the B, we just throw a minus sign in. We throw a minus sign in and we got the recipe for the theta, right? So basically you take that recipe that we got for the B, which is right here, and you throw a minus sign in and you've got you're pretty much the same recipe. Oh, you have the correct consistent recipe. Now notice, you could say, well, should you have changed the plus minus to minus plus? And I'd say, well, yeah, you could, but it doesn't make any difference, right? Because it's saying the same thing. Whether you write it minus plus or plus minus, you're still adding and subtracting pi. If the AN is negative. Okay, and we take a look at the recipe that we would have. The recipe that we would have for that angle, and we see, in fact, this is consistent with that. Any questions? Okay. All right, so we actually got done with now the representation for the compact trig case and the recipe for the coefficients in terms of the ANs and the BNs. Before I forget, and I'm tendency to forget things. Before I forget, let me mention, I did open the floor to questions on that homework 4. Just so you know, I'll post a quiz that you can work on it. I mean, our quizzes are almost always going to still be the same. They're just going to be a sample of what you would need to know, let's say, from that homework on an exam. It's not intended to be comprehensive. So just so you know, I'll have a quiz ready for you to take no later than today's Wednesday, no later than Friday. Okay, it'll be there on Friday morning. And then the idea being you don't have to finish it, and it'll be due like on Monday, you know, so it'll be, and I think that's reasonable. Not intended to be a long quiz. It'll be intended to be, if you want to gauge yourself like a typical quiz, if it was done in class, I would design it in such a way that 15 minutes should be enough to do it if you know what you're doing. And if you don't, well, that's where you go back and you check your notes, hopefully. Okay, so I got that clarified. Any questions on that last part?
So the quiz is going to be online?
Yeah, got it. I mean, I'm not a fan of, we're going to have to do an exam that's not also online. I mean, let's put online. It's online in the sense that it will be posted on Canvas. You will presumably do it, you know, if you elect to do it, like make a hard copy of it and write your solution, somehow get an image uploaded, just like the one for 4308, and get it in time. Deadline.
Okay, so like a take-home quiz?
It's like that, yeah. I don't want to go through the in-class quiz thing. That's just for a quiz. It's too much. Now, for an exam, that's a different story. When I say
Oh.
in class, where I actually watch you, I'm not going to do that.
Okay.
But for the exam, I have a slightly different method in mind, which we'll talk about. Okay, so but you're clear on the quiz part, though, right?
I have a question about it. So we would have to print it out, write the solutions on, and upload them, right? Would there be like some sort of well, would the time limit on it be similar to the
No,
last?
I can't. I mean, the fact is, why should I do that? Because I can't police that.
Oh, okay.
You know, let's put it this way. You know, this is really a judgment call on your part. You know, if it takes you all day to do it, then it tells me that you're really not studying the homework the way you should. You follow me? In other words, if you really studied the homework the way it should and took opportunity to ask the questions when you need to, you know, the idea would be, well, ideally you would finish it in 15 minutes.
Right.
But if it takes more time to get it done, which I don't hold it against you for doing that if you need to, but just bear in mind, it's not the best sign for being ready to take a full exam. You follow me a little bit on that or not? I mean, in other words, it's supposed to give you the feedback whether you're getting ready for the exam or not.
Yeah. Makes sense.
Okay. Okay, hopefully that took care of that question. All right, so I think we could time. Well, let's knock out the third one right here. We can do that. It's only one page. Okay, for the exponential Fourier series, I think we're ready to rock and roll on this one. The exponential Fourier series.
Can you refocus the camera?
Oh, I can. What happened? Has it been upside down or what's wrong with it? Let me see. Looks like no, it's right side up. Okay, I couldn't. Okay, so what you're seeing? Okay, I was worried.
It's just really blurry.
Oh, is it? Okay, you know, I'm glad you brought that up. I see. I can't. To me, it looks pretty clear, but I can't. Is it any better now? Or tell me.
Better.
Is it better?
Yes.
Is that better yet, or worse?
Zoomed in.
Better or worse?
It looks better. You just zoomed in a lot.
The last one was. This one's the best one, right? If that's all I need to know. I mean, if you're happier with that one than the prior, then we'll stick with this one.
Yeah, you'll just have to make sure that it's in view whenever you're pointing at stuff.
Yeah, that's hopefully. Well, see, now that's why I've got the screen up. I should be able to tell what I see is what you see, right? At least on the video screen here.
Yep.
Okay, so let's start from the top on that then. Now, so the big idea that is behind all this is in many ways the same, okay? In the sense that you know, we have these sort of representation idea, and where we had the sines and the cosines and the constant. Now, when it comes to what's called the exponential Fourier series, our basis would look like, could and does look like this. In other words, it's made up of complex exponentials, where the time dependence is controlled by the essentially with harmonic factors, right? So the fundamental and the harmonic. So you would have, let's say, an e to the minus j omega naught t and e to the plus j omega naught t.
Class one.
And then you have this, again, this one is very much like the one that we had. It plays the same, it's actually the same, plays the same role as the one that we had here when we did the basic trig. Remember, we had a 1 there, represent the constant 1. And so, I mean, if you think about it, well, that's the function, which is just simply the constant 1 for all t. And that's it right there. And then the other ones are like, they have time dependence, that's clear. And each of them is made up of, if you use the Euler, has a cosine and a sine piece, but we don't need to show that explicitly, but it's there. And so what we're saying from a representation viewpoint is this is a complete set in the sense that it's sufficient to represent any time domain periodic function. And all we have to do is come up with the recipe for the coefficients for the complex Fourier series, exponential. Now, throughout all this, really, it's the same inner product rule can be still used, okay, concept-wise. And our approach is very similar. So the good news is we don't have to do the ANs and the BNs separately because we only got this one set DN. So what we're going to find out is that the this one rule will in pretty much one step we get everything we need. How are we doing on time? We get time. Okay, so imagine again we have that dot kind of represents the operation called the inner product, and we'll do the inner product of one of these, okay, and if you look carefully, I guess it would be it's some arbitrary one on the positive side, okay, you know, because there's no negative there, I guess it'd be on the positive side. And notice what changes when let's see. What changes as you move to the right is the integer in front of the omega naught t. So basically, as the integer goes up, you're going to a higher frequency or a higher harmonic. And so we're going to take an arbitrary one, let's say on this side, and imagine what happens, even though in the end we'll say that the recipe applies for all the DNs, we'll see. But anyway, let's just say, and we can imagine it, and then we do this inner product coming in from the left. Now, the important thing to notice, just like when we did the ANs before, you may remember that we did the ANs before. We were real careful because we did this inner product with a cosine of n prime omega naught t, not to be confused with the n that we're doing the sum over, right? And so I'm kind of playing off the idea we already seen, and so we're using an n prime here, which is not the same as the n that was originally in the series. Any questions? Okay, so in implementing this inner product rule, now this is the one time I could say, when you can see it too coming, I think, in the one time where this complex conjugate makes a difference. And that's because, of course, the complex exponential being complex, taking the complex conjugate will change it. But fortunately for us, to change it in an easy way, because all we have to do is think of replacing J with, anybody out there? Replacing J with?
Minus J.
Minus J, correct. So if we replace the J with a minus J, and you can see that happening, that plus J n prime became a minus J n prime. And then the part associated with the, since it's a linear operation, the inner product like a linear operation, that means we can move the operation past a sum, past the constants, even if they are complex, and just let it operate on the part that has time dependence, which we see is buried in that complex exponential right there. So what happens is, as you let that operation distribute through, and where it has to be fundamentally effective is where you hit a part of that expression which has time dependence, that part right there. So what we need to do is, then when we do this, we need to remind ourselves, well, complex conjugate means replacing J with minus J, and that means we can take advantage of the fact that we're taking the product of exponentials, and when you take the product of the exponentials, what do you do to the arguments?
You add them together.
You add them, right. So when you do the algebra on adding the arguments, you end up with n minus n prime there, right? So there's really two cases that we're interested in, kind of like before. If n is not the same as n prime, then n minus n prime won't be 0, but will still be an integer, right? Because that's the nature of the assumption, is this n prime could very well be one, could be, and no doubt would be one of those n's, but not a general one. So you would expect that n minus n prime in most cases would be not 0, and yet they're both integers. So the difference of two integers is still an integer. Did I say that too fast? Any questions?
No, sir.
Okay. So now if you replace the n minus n prime with this integer, then you can write the integral that we need to do would be that, the integral of that. And we can, in fact, then replace the e to the j m omega naught t with this right here.
I think somebody has their mic on.
Yeah, something's going on. I don't know. Can anybody check and make sure? Yeah, here's something.
Yeah, here's somebody's
Christian.
TV.
I'd rather not. I don't know who would be.
I
though,
think
but
you may have the power to mute him. I'm not sure.
trouble is I don't know who him is.
It's Christian.
Oh, is it? Okay. Well, we can test that.
All right. What does it mean for you to get back? We're out here in a charity golf tournament. Tell us about that.
It's just such a great honor to be part of it and this foundation.
Let's see, going the other way. Should be here. If it is him, he should be in here somewhere.
Relaxing. So can we
That's strange. I'm not seeing his
you ready to
name.
go?
It's the one with a picture of a dog.
Relax out here on the course, just enjoying the time watching everyone else talk and talking and I'm getting healthy at the same time while enjoying myself. So that's pretty cool.
Well, thanks for talking to us, Rob. Thanks for Class X for us.
Thank you for having me.
No, what's the last name I should be looking for then?
I think you can,
I can mute everybody.
yeah, I guess you could mute everybody and then you can, I guess, unmute everybody.
Well, it's seems like it might be a possibility. Let me, it's always good to know how to do these things. Let's see.
Yeah, that worked.
Okay, seems like it's gone away. All right. Next time I have the guy in here, I'll try to find out how to do the muting part of it. Okay, so if you simply do the integral up here, remember replace the n minus n prime with an m, then really you expand the complex exponential, you get the cosine and the sine, but essentially these are just sinusoids. And since the T naught, they form the harmonics of the fundamental, and you may remember that the argument for that they're going to be zeros based mostly on a picture, although you can probably do it analytically. And that's basically by integrating those over an integer number of cycles, both terms would integrate to 0. So in the end, what we're saying, well, when n is not equal to n prime, then we're going to get 0. However, if n is equal to n prime, okay, then n minus n prime is 0, and then you're just integrating the dt over a time interval t naught, and that gives t naught. So you can combine both of these results conveniently using what's called the Kronecker delta. And I think you may have seen this before, I think along the way, but not too often. The Kronecker delta is more or less for discrete problems. And the idea being, well, if n is equal to n prime, then they're equal, the integers are equal, and that's equal to 1. And if n is not equal to n prime, it's equal to 0. So we can use that idea here. So what we're saying is in the end result was this quantity became T naught times the Kronecker delta nn prime. There is the T naught Kronecker delta nn prime. And we know that if n is not equal to n prime, what's the result? What should I write here?
0.
0, right? And that's for n not equal to n prime. However, for n equal to n prime, what do I write?
T naught.
T naught, correct. So the fact is we have this long infinite sum, but essentially all the terms are 0 except for one term. And that one term is when n is the index, when the index n is equal to n prime. Now, if the index n is equal to n prime, then this becomes dn prime. And then you get T naught. So our objective was to solve for the recipe for the coefficients. And so we see, in fact, that there's only one term in all those terms, and that would be the dn prime T naught. And so if we write out this is where we started the business up here at the top. If we write out what that would mean, and we've done this already because the first term you replace the j with a minus j, therefore the minus, and then there's the x of t. And then so if you want to solve for the dn prime, can you see that? I mean, can you solve for the dn prime? If you solve for the dn prime, then you just need to divide by the t naught. And here's the recipe that you get. Notice the minus sign here, the minus sign there. And if we check our table for the recipe associated with the exponential Fourier coefficients, and let's see if we can blow that up a little more. I think you can see that there's a minus sign right there where it has to be. Any question on that? Oh, one last point. Okay, we did the same trick before and I jumped over it without saying anything. When all is said and done, you get a recipe for dn prime. But n prime is just a parameter, okay? So we're older and wiser now. We know that that we can change one symbol for another, and so we just drop the prime basically to simplify the notation. And for that purpose, we get the dn. Any question on that? All right, how much time I got left now? Let's see. A couple more minutes?
Like a minute.
What, a
Less than
minute?
minute. Yeah.
1 minute, okay. Okay, let me tell you where I'm going so you can read ahead a little bit. Hey, wait, what we have here is actually we can do one thing. 1 minute's about enough time for what I want to do here. Okay, so imagine I'm computing the a sub n's for the basic, and here's our recipe. If the a sub n is equal to 0, can I make any comment in terms of knowing what is the symmetry for x of t? And let's say I happen to know that x of t can be either odd or even. What symmetry of x of t would guarantee I get a 0? Odd or even? Now, bear in mind that we have symmetric limits here. Okay, I'll let you think about that. I'll pick it up on Friday.
I think it's gonna be even.
It would be what?
Even, I think so.
And any other guesses?
Odd.
Yeah, I think
There we
either.
go. Okay, odd's the right answer. I'll let you think about that. All right, we'll pick this up on Friday. I won't just jump over that subject. We'll pick that up. I'm not here for a few more minutes if you have questions. Otherwise, I'm going to shut down the meeting and go home.
Professor?
Yes, I'm here still. You have a question?
Yeah, did you go over on finding the expression for AN again?
Oh, okay. Yeah, I mean, the one I did last time, right?
Yes, last class.
Okay, sure. I've got those notes here. I think I posted these on Canvas, but let's deal with your question if we can. All right, so would help me answer your question if you can kind of direct me where you're confused, or I could start from the beginning, but I'm not sure that would be. And let me back out on that here a little bit. How come I should be able to get that? Oh, here we go. Okay, so I'm backing out a little bit. Where is the heart of your question? Is my point. I don't want to.
Just in general, like the whole thing, I guess.
Okay.
From the beginning.
Okay. First off, I'm going to say this. We went through some discussion setting up these rules right here in this part. Okay. And in many ways, by having these rules written down on the page, really did expedite the argument for solving for the A sub n. Now, so in response to your question, I would say, if you're comfortable with those, then I'll take it from there. And if you're not, I'll back up.
Yes, I am comfortable.
Okay. All right. So then that actually turns out that means it should go pretty fast. But you stop me if I go too fast. All right. So what we did was our objective was to solve for the recipe for the A sub n. And we can see that the A sub n are the coefficients for the cosines, not for the sines. So with that in mind, I anticipate that since I'm interested in the A sub n, not the B sub n's, that it won't do me any good to multiply through by the sine n omega naught t here, because when I do that, all of these are going to go away. So I've got to find a way to when I say multiply through, to do the inner product through, find a way to select one of those ANs, which would lead to a recipe. And the idea is, well, it's going to be it's going to be a cosine. So if I do the inner product from the right going in, as we see it here, then I would do the inner product on the first term, and there's only one term there, and then I would do the inner product on the sum that I have here. But the inner product being an integral, would have these properties that it's like a linear operation, which means it moves the operation of sum. The sum of the operations means I can move it past the sum. And also the property on the operation of the constant times the function is going to be the constant times the operation of the function, so I can move it past the constants. So in the end, the inner product with this cosine of n omega naught t ends up only, you can think of it only operating with the cosine of n omega naught t. Now this is about your question. So if you have so if that's not clear, you need to tell me.
That's clear.
Oh, is that clear? Okay. And so we see it, we argued that from the top here, since this is for any integer n, this is going to be true. Therefore, we were able to set this one to 0. And for any n and m, this is going to be true even when they're the same. That's why we were able to set this one equal to 0. And it doesn't matter what n prime you pick. And we know, I say from up here at the top, as long as n is not equal to m, okay, this would be true. So we would say, well, we can say, well, all the terms, remember n is the index here, all the terms with n in it, the only one that has a hope of not being 0 is when n is equal to n prime. Because our rule up here at the top says if n is not equal to n prime, that would be 0.
Right.
And so if that's clear, then I feel comfortable going on. Is that clear?
So right there, n is equal to n prime.
Yeah, that's the idea. Is one of these n's of the infinite n's that are there, one of those n's is going to be the same as the n prime. Even though n prime is just a symbol, if it makes any help, think of it as like a particular number like 5. And yet we know this n here has to go from 1, 2, 3, 4, 5, etc., all the way to infinity. So that is somewhere in going on from to infinity, one of those n's will agree with the n prime, but only one.
Okay.
Is that okay? So
Yes.
okay, so on the right-hand side, then what we would have is we would have a 0 from the constant, okay. Then we would have almost all of these are 0 except for possibly, and we expect one of them will not be 0 when n is equal to n prime. And when n is equal to n prime, then we have to change that a sub n to a sub n prime. We see it here. And then we can do the cosine of n prime omega naught t cosine n prime with the inner product cosine n prime omega naught t.
Okay.
Okay, so far okay?
Yes.
And the last one is 0. Okay, that's
Right.
okay. So now this is all we have left. Okay, that on the right hand side, now we just got one term, which is kind of where we wanted to be. And so if we can evaluate with that inner product of cosine of n prime omega naught t with itself, then we can put that in there and then solve for the a n prime. But it's not obvious at that point, but down below, I have a few lines which I think we briefly covered. So if we write what that would mean using that inner product rule, and like this is my F complex conjugate, but since it's real, I don't care about taking the complex conjugate or not, it doesn't matter. And this is my G. So we put in the F times the G, but since they're the same, it becomes simply cosine squared n prime omega naught t dt. And then using the trig identity, cosine squared x is 1 plus cosine 2x over 2. That would be 2 n prime omega naught t divided by 2. Now, since this is there's a 2 in the denominator, but you can break these up into 2 pieces and think of a constant plus a sinusoid. But since you're integrating over a time interval equal to the fundamental period, that means that we're back now to a situation where it's kind of like this, where it would be 0 because it's an integer number of cycles.
Okay.
And therefore the only thing that survives this would be the 1/2 dt integrated over a time interval t naught. So the integral dt from minus t naught to t naught or 0 to t naught is going to be t naught over 2.
Yes. Okay.
And so what these two lines show is we can replace that inner product with simply t naught over 2. Okay, and so the idea would be, well, once we did that, we can then solve for the a n prime, which is what we want to do in the first place. We want to have so we solve for the a n prime, by dividing both sides by T naught over 2. And since this is the left-hand side that we started with is this right here.
Yes.
And there it is right there. And I divided by T naught over 2.
Oh, okay.
And then I wrote out what that means in terms of the definition of the inner product. And just simplified a little bit by taking what's in the denominator to the numerator. And so in the last step, it's just like the last step we had regarding the complex exponentials, is that, well, the n prime is just a symbol for an integer. We can make it we can simplify the form a little bit by removing the prime, and we're good to go for that. And this is how we got that one. Is there a question?
Can you go back to the previous page?
Sure.
I guess the part that I'm still having trouble with is on where the cosine of n prime omega naught t is.
Okay.
But where it's multiplied to x of t. Top. Go.
On the left, you mean?
Yes. At the
Okay.
top. At the top.
Go up.
Go up. Yes.
Keep going up.
Down.
Down.
That one.
That one.
Yes. Where you say that you move it to the right or to the left.
Yeah, I think the way I view it is the way it looks like I'm bringing it in from the right.
Yes.
You know, I mean, you could have done it from the left and the answer would still been the same, but you have to choose one or the other.
So you're moving the cosine of n prime to the left, or you're moving it to the right.
I mean, the fact is, I'm saying coming in from the right. I don't know which way I say. Coming in from the right.
Oh, okay.
Basically means that I'm putting that one on the right-hand side. Okay, as opposed to the cosine of n prime omega naught t inner product x of t, which would have been the reverse. Now I could have done that. I mean, because it will work out the same. Just I had to choose one. So I chose this one. Coming in from the right. Going to the left. Did that still confuse you or not?
I think.
Because you can see I've got it on the left here. I've got it on the left there. I've got it on the left there. I'm going to say left. I mean, I've got it. It's coming in from the right. I keep saying left. It's coming in from the right on all three of these.
Okay, so you're moving that one.
Yeah. So imagine it's coming in from the right on all these terms.
Okay.
So it's coming in from the right there. It's coming in from the right on this one. It's coming in from the right on that one.
Okay, makes sense.
Did it get, after all that did it get clearer for you or not?
Yes, sir.
Okay. Yeah, I mean, is that?
Yeah, I think that was it. That was just my question.
Okay. Well, I mean, it's a good question. I mean, I think if you start to see this one, then the other ones kind of make more sense. I mean, it's sort of, they're the same. We're really doing the same thing. Now, we didn't go through all the details on the sign, but it's really going to be, it would be the same method, except for instead of coming in with a cosine n prime omega naught t, you'd come in with as you might guess, a sine n prime omega naught t. And when you do that, it essentially, all these end up being 0. That one, of course, 0. And then you end up picking up one of these. One of those BNs, one of those n's from the BN become an n prime. And then that matches up.
And that's for finding Bn?
That's for finding the Bn. So without really going through all those details again, I just gave you what would happen if you did that.
Oh, okay. Okay, that makes sense. I think I got it then.
Okay. Okay. Good.
Yeah, I was just having trouble understanding that part.
Well, it is a brand new idea, no doubt about it. So, but there is a consistency to this, and all I can say is, any other questions out there? If not, I think I'll end the meeting.
I think that's it.
Is that it? Okay, I'm ending the meeting. There we go.